Today I'm going to present a paper Sensing the Noise, Uncovering Communities in Darknet Traffic that was realized in the Smart Data Interdepartmental Center of Politecnico di Torino in Italy. First of all, I'll start with a bit of background and terminology. One thing that we need to specify when dealing with darknets is that they have nothing to do with the dark web or deep web concepts, but in this case, we define darknets as a set of IP addresses that are advertised without answering any traffic. So by passively recording this kind of traffic, we can assist on network monitoring activities and cybersecurity purposes. The concept of darknet is similar to a sort of set of mailboxes in the desert, meaning that they are not related to any proper household and they only receive unwanted mails. In the same way, the traffic hitting the darknet is unsolicited by definition, and it is useful for cybersecurity and network monitoring. In literature, we find research papers that use this kind of traffic to spot misconfigurations, identify distributed denial of service attacks, analyze the internet censorship during specific events, or estimate the IPv4 address space utilization. Our research question in this paper is can we use darknets in order to automatically detect coordinated events happening on the network and use them as a first sensor to trigger some alarms for what's happening or what may happen also in live network. But what do we mean by coordinated events? We can have malicious coordinated events like, for instance, botnets. One of the most famous example in the recent past is the Mirai botnet, targeting especially IoT devices. But we can also have internet-wide scans that were made for research purposes. In a previous work, we were able to analyze two IPv4 darknets of different size and different geolocation in order to try to characterize this traffic and highlight the differences and similarities. What we found out by starting to check the time patterns of these darknets was that even if we tried to remove the noise, so we only addresses the top talkers addresses, meaning the sources that produced 10 flows at least in 1 hour bin, we see that the number of packets is still very noisy and irregular, and it is very difficult to find some similarities over the different darknets. But if we enrich the informations we have with, for instance, the mapping of the autonomous system source, what we find out is that a very large amount of packets hitting the darknets is produced by a small number of IPs, and some of these IPs appear over all the darknets that we analyze. For instance, this autonomous system source targets the Italian darknet, the Brazilian darknet, and also the Dutch darknet that we used for reference. So starting from this information, we begin to wonder whether there is an efficient representation of darknet traffic in order to ease this analysis and start to automatically detect this kind of coordinated activities. But in particular, when looking for an efficient representation, we started to wonder how to represent the relationships between nodes, sources and destination, what do we mean by common behavior, and how can we filter noisy traffic. We engineered a pipeline which starts from a graph definition, then proceeds with a noise filtering technique, and performs then community detection on top of this graph. This is an example of what we expect to get. So graph linking sources and destinations is turned out to be a viable solution for our problem. and grouping together nodes, what we expected to detect were, for instance, botnet infections or other kinds of scanning activities. As we said, a crucial point for the graph definition is to find a meaningful representation for darknet traffic. Considering that the darknet traffic is unidirectional by definition, we chose to represent it in the graph by using a directed graph, which is also bipartite and weighted. Bipartite because we have, by definition again, two kinds of entity, a source and a destination. Sources and destinations can be aggregated at different granularities. For instance, we can choose to aggregate the sources in terms of IPs, in terms of ports, autonomous system, or subnet. And again, we can perform the same for the destinations. The choice of the kind of nodes, source and destination nodes, is a trade-off between the graph size and then the complexity of the calculations that will follow, and the information relevance and interpretability. We did several attempts. For instance, over 1 week of data from the Italian Darknet, we tried to extract a graph linking IP sources and IP destinations. In this case, we had a precise representation on the sources, but the graph was really complex to handle because it could reach up to more than 200 million of edges. The same holds for a port-to-port graph. It is again too complex, and we lose the information about the origin entity. So, as a trade-off, we tried to define a graph containing as a set of sources the set of origin autonomous systems, and as a set of destination the destination ports. Every edge between a source and a destination is weighted by the number of packets the source directed towards this specific port. The noise filtering in this case is still kind of an open problem. For this preliminary work, we decided to include in the graph only the autonomous system which sent at least 100 packets in 1 week. So we removed the non-heavy hitters autonomous systems. On top of this graph, we tried two community detection algorithms, the label propagation and the greedy modularity. The results yielded by the label propagation were not suitable for this kind of graph, which is still very densely connected, and this algorithm was basically merging all the nodes into a single community. On the other end, the greedy modularity turned out to yield some very promising results. The main idea behind the greedy modularity algorithm is to look for a group of nodes which are strongly connected among each other and loosely connected with the rest of the graph. Of course, we have to find a measure for this kind of strong connection, and the measure is the modularity. In our graph, modularity goes from 0 to 1, and the higher, the stronger is the connection. The algorithm evaluates the modularity iteratively. As a first step, it labels all the nodes to a different community, so the cardinality of the community set and the cardinality of the vertices coincide. As a second step, all the neighboring communities are merged together, and we calculate all the gain in modularities. We choose to keep the merging as a third step, where the gain in modularity is maximum, and we repeat steps 2 and 3 until the gain in modularity is null all over the graph. In our specific case, every packet of the trace gets 2 labels according from the point of view that from which we observe. We have a source label, so autonomous system community, and a destination label. So every entity in the graph will have this twofold labeling. For instance, if we consider community C3, and in particular we refer to this source, it will have a single autonomous system community, which is C3 itself, but the port community will be twofold, because some of the activity of this source is directed towards the C3, and some of the activity is directed to C1. In the same way, this target in C2 will have a single port community, which is C2 itself, but it will have several autonomous systems community, because the sources hitting it are coming from C4, C2, and C1. This is an example of the results that we expect to get. For instance, here we see two very requested services on top of the Italian Darknet. We were able to generate a total of 18 communities. More in detail, we see that communities IT4 and IT0 are the largest in terms of volume, both taking a look at the source's point of view and at the destination's point of view. But receiving the largest amount of traffic doesn't necessarily coincide with including the largest number of autonomous systems of ports. If we take a look at the scatter plot, we see that, for instance, IT3 shows a very interesting pattern. It includes a very large number of ports and a very small number of autonomous systems, meaning that the sources included in this community are performing what we call an horizontal scan. So they are targeting a very large set of destination ports in order maybe to look for some vulnerable services. On the other end, we have the vertical scan patterns. In this case, IT1 includes a very large number of autonomous systems targeting a very small number of ports. So probably the sources included in this community are really willing to find vulnerabilities or to access services over a concentrated set of targets. These results are better visible if we take a look at this heat map. For instance, if we focus on community IT2 and IT1, we see that the traffic directed towards the top 50 ports that we see in the trace is very distributed over targets. And in this case, we talk about horizontal scan. On the other end, if we focus on IT4 and IT6, we see that a very large volume of packets is directed towards single or just a few specific targets, and this is exactly the pattern of a vertical scan. From this heat map, we were able to extract some time patterns. Here again we see IT4, which is the largest community in terms of volume. We see that in general the targets are the ones that we highlighted, and the traffic is very noisy. Together with the two targets that we already underlined, there are some other very common requested ports like SSH and Telnet. While a more interesting pattern is the one we find in IT15, in which we see that the algorithm was able to automatically detect the requests performed by some sources towards a set of adjacent ports, which most likely belong to the same framework. And we have to underline that when trying to detect this pattern, we didn't need any manual intervention. So community detection is a viable approach when it comes to the detection of coordinated events. We presented some promising results coming from the GMA algorithm that of course can be further tuned, and we expect them to be better in the future. especially when targeting the noise filtering aspect, which is in this paper still critical. And we believe as a future work we will be really able to fine-tune also this aspect and make a more automatic noise filtering criterion. And with this I conclude. Thank you very much for your attention, and I'll be glad to answer to your questions.